Welcome everybody to this lecture number 7 of the summer school on dynamic deformation of solids. Today we're happy to welcome Irene Beyerlein, who will be telling us about the basic mechanisms of twinning. Irene Beyerlein is a professor at the University of California at Santa Barbara. She received her PhD from Cornell University. She's a highly prolific and highly recognized scientist. In 2013, she received the Los Alamos National Laboratory Distinguished Postdoc Mentor Award, indicating her commitment to mentorship. And in 2012, the Los Alamos National Laboratory Fellows Prize for Research. Her interests are in mechanical performance of advanced materials via multi-scale understanding of processing microstructured property relationships. We're very happy to have you here for this lecture. That's my introduction. So now please go ahead and share your screen and we'll continue from there.
Okay, great. Well, thank you so much, Mike. Thanks for having me speak today. And first of all, I want to make sure everyone can see my screen. Can you? Yes, so I'll just take that as a yes. So first of all, I want to say that this topic, deformation twinning.
I cannot.
Oh,
I don't know if anybody else can, but I cannot.
No, I just see a dark screen.
Oh, let me. Okay, so let's see. Let me go back. Screen share. This. All right. So now, let's go.
Yes.
Are we good? Let's see. All right.
Yes.
Wonderful. So yeah, as I was saying, so this topic is a rather important one, but it's perhaps one that you're not familiar with as far as reading about it in a textbook or having a course on it. Deformation twinning usually gets encountered by researchers in the material science field because it's relevant to their particular research area or to the class of materials that they're working on. But I'd like to say that, so I hope that this lecture gives you a good introduction as to why it is important, and especially for metals, and also why people continue to research this field, even though it's been introduced for about 100 years. It's an interesting one. So it does make for a good mechanics problem, and also for a good material science problem as well. So hopefully there's something in it for everyone here. And also I want to thank you for being here, and for those of you that are seeing this on YouTube as well. So with that, let me just kind of give you an idea of physically what are twins. And when we think of twins, we think about their physical properties and in a particular length scale at which they tend to manifest, in which they're most commonly studied, and that is at the mesomicron scale. So here I'm just showing you some microscopic images of twins. So the twins are what you see here are these there are these lamellae, and they have this high aspect ratio. Let me just put on my pointer here, that may help. So so here we have a picture of copper. You can make out some of the different orientations. These are grains, and within the grains, you can see that there's these well-defined, planar, rather straight-looking boundaries. So these are twins. These are twin lamellae. So these grains have several twins within them. Here's another material that commonly has twins, as magnesium. In this case, they're not as planar and structured as what you see here in the copper, but they have this high aspect ratio, and they're in rather planar type boundaries. Also, these are two metals. I want to bring up that they don't necessarily always occur in metals, but they can also occur in nature in different kinds of materials. I thought this was interesting. This was a exoskeleton of I think of a bug. So I thought this is interesting. This, of course, isn't what we're going to be talking about today, but just to let you know that they do occur in other materials. Here we have boron nitride. This is a particular nanograin here of boron nitride, and again, you see these nice lamellae. These are twin lamellae. Also, there's been this interest in twinning that was revived with the advent of nanocrystalline materials. Some materials that normally wouldn't twin if they're coarse grain are found to twin when you in highly small spaces and these nanomaterials, for instance, in this copper material here. And in magnesium as well. So that's generated some interest that this mechanism occurs. And of course, there are some rather complicated materials where sometimes the only mechanism that's easy for them to form is by twinning. So this is a rather exotic material that normally people don't study, but it's if you ever want to study twinning, uranium is probably one of the best materials to study it in. So this just gives you a feeling of what twins are, what physically what we're talking about. But as far as just some basics, I mean, so I've shown you different manifestations of twins. Now, the origins of twinning can be from growth, which we saw in the nanotwin case in copper, or from deformation. So what we're going to focus on here for CREDDS is deformation twinning. So these twins were induced because the material is being deformed, and they are mechanisms for accommodating deformation. They're not exclusive to any particular class of material. They can actually occur in many different types of materials. And as far as deformation twins, and in particular ones that occur in metals, you would find deformation twins in crystal structures of all types, from face center cubic, body center cubic, hexagonal closed pack, orthorhombic, and B2. And these are just some examples of the different kinds of crystal structures in which we can see twins. Also, different metals and alloys. The effect of alloying is actually interesting. In some metals, certain alloys will promote twinning, and others alloying would hinder it. So you see these in different types of materials. So again, not exclusive to just pure metals or to particular alloys. Now, as far as when they occur, it's usually twinning is not exclusively the only deformation mechanism that the material would be using to accommodate an applied load or applied strain, but it also occurs in competition with plasticity or in dislocation slip, which I think was a topic of last week's lecture. So that lecture is relevant to this one in particular because twinning is usually occurs alongside plasticity or slip. And what we find is that in that competition, that you can see that in some materials, slip would dominate over twinning. So when does it occur? Does it occur when you have that we're concerned with CREDDS, or at low temperatures or high temperatures? Sometimes it occurs if you deform the material in one sense versus another, and sometimes you can alloy the material to have it twin more so than with the pure metal. And so all of these have been the focus of, all these effects have been the focus of studies and research over the past, I would say, at least 50 years. And what you find is that there are some general trends, and we won't go too much into those trends, more into the basic physics of how twinning occurs. But just so you know that that still it's an empirical phenomena at this point as to when a material will twin and when it will not. We're not at the stage in understanding as to knowing why certain materials would twin more than others as the strain rate would change, as the direction of straining would change, etc. But it's so in one material you may test it at one temperature, one strain rate, and not see twins, but that doesn't mean that at another temperature, another strain rate, it would not twin. So it's very sensitive to these apply loading conditions. So some common features among them is somewhat of what I had discussed in the previous slide, is that they do manifest as a particular volumetric domain within a crystal. And so they're very easy to see and analyze. So that's probably the easiest part of deformation twinning. And when they do occur, they are a domain that has a different orientation. So they will introduce subcrystalline boundaries, as you also saw in the previous slide. And that misorientation across that twin matrix boundary, if you will, is typically a theoretical precisely defined one. So that is also one way in which you can characterize different types of twins by analyzing and determining the misorientation across that boundary. And something also to remember about twins is that they are a deformation mechanism. So while when we see them in images, they appear to be these misoriented domains within crystals, that they are actually shearing that material and rather intensely. And so this is something that has now been able to be measured with different types of in situ straining techniques. But theoretically, we can understand the amount of strain that each twin can incur based on the type of twin it is and the volume of that twin. So with that, let me now, and now to mention that, so while we could learn about twins and different kinds of crystal structures, this will be focused on deformation twinning in hexagonal closed packed metals. And the reason for this is that in hexagonal closed packed metals, twinning is a prevalent mechanism. So you don't need extreme conditions like extreme or very cold temperatures in order to see a large amount of twins. And so it's been a nice material class in order to study. So just a little bit about HCP materials or hexagon closed packed materials, just to give a small background as to why twinning is prevalent in these kind, is that I want to just give just in the next 3-4 slides what they are. So hexagon closed packed metals refers to a atomic arrangement of their crystal structure of metals that where they have their closed packed planes have a hexagonal arrangement of the atoms. So this is like the closed packed plane here. This is the crystal structure. So we can see here this closed packed plane of this atomic lattice. It has a hexagonal arrangement. That these closed packed planes have between the atoms is referred to as the A-axis or the A-dimensional lattice. So that's the lattice parameter with the closed packed plane. Now the distance between like closed planes is just assigned to the C-axis, and the C-axis is not equal to the A-axis. So in most metals, that's A-axis. But that C to A ratio spans from about 1.5 to about 1.8. Some examples of some common structural metals and then for the pure form. So magnesium about 1.6, titanium 1.6 as well, titanium again. So there's they're all about 1.6, but see that means that this arrangement is a low symmetry arrangement of atoms. Now this is in contrast to, let's say, two of the other common crystal structures for metals, face center cubic and body center cubic, which you may be more familiar with. And so you could, this is a much more symmetrical case, but this is low symmetry. It's called a low symmetry crystal structure. And because of the low symmetry, this is where twinning then becomes a rather prevalent mechanism. So I just want to give you also an example on the periodic table here, some of the structural metals that have a HCP structure in ambient temperatures and pressures. Beryllium, magnesium, titanium, zirconium, for instance, zinc, cadmium. These are just some of the examples. So these and their alloys have an HCP crystal structure. Why there's been some interest in this class of metals is that they do have many interesting and important intrinsic properties that make them valuable for structural applications. Such as that they have a high strength to weight ratio. Some of them are biocompatible. Titanium, for instance, is relatively fatigue resistant, and they also have radiation resistance. For instance, zirconium pretty much bought up by most of the nuclear industry because of its good nuclear properties. So going right into it, so we want to include more HCP metals in applications, but why are they not seen as much as we would like? And it largely has to do with their complex mechanical behavior. And so particularly what I'm referring to is that they are highly plastically anisotropic, so which means that their deformation response significantly depends on the direction of loading, more so than, let's say, a metal that has a cubic crystal structure. So just giving you some examples of just some pure metals that have an HCP crystal structure, such as titanium, zirconium, and magnesium, for instance, that you can see here that just by, in this case of titanium, just by changing the direction in which you load it, you have a remarkably different hardening rate and flow stress. Same with zirconium. This is sheet material. If it was deformed in plane, it has a rather low yield and flow stress, but if it's deformed through thickness, you see almost 3 or 4 times increase in strength and flow stress. So this anisotropy makes it very difficult to form and shape and also predict the behavior of these materials. They also are very sensitive to conditions like strain rate and temperature, where you can see vast differences in their flow stress and yield stress, and also just in hardening behavior. Now, the reason why I bring up some of this is that twinning is partly responsible for a lot of these sensitivities. Now, if we look here, why is it that these materials have a large plastic anisotropy? Can be explained just qualitatively by their atomic structure. So if we go back and look at this hexagonal closed packed structure, you can see that the basal plane, which is this high impact plane, this high atomic density plane, this plane is the easy glide system for most HCP metals, but its slip direction, or Berger's vector, lies in plane, so it can accommodate any deformation of this crystal that's along that direction. Similarly, there's depending on the C/A ratio, it may be that this side plane, or what we call prismatic plane, would be the atomically higher density plane, and therefore be the more favored, tends to be the more favored slip system, and that's the prismatic slip system. So these two are alike in that they also they accommodate the deformation in the same direction. Now, however, a crystal needs to be able to deform in both A and its C axis. So along the C axis, deformation is also critical. And there is another slip mode or slip systems that could accommodate deformation along the C-axis, and that's called the pyramidal slip system. Now, because the atomic density can be rumpled in this case, or a lot rather dispersed, that sliding in this slip system is much harder than it is in the A direction. Now, the difference between this easy and hard mode of slip controls how plastically anisotropic that material eventually is. So we can see this qualitatively if we think about if we have this crystal that's oriented in this direction under one load, then in this load, the orientation relationship between the loading direction and the orientation of this crystal would invoke slip mostly on this easy slip system. So you'd expect that if you're deforming this crystal in this direction, that it would deform rather easily, would have a rather low flow stress. However, if I just keep the load direction the same, but I now have a different orientation of that crystal, it would, in this particular case, it would need to deform by pyramidal slip in order to accommodate that deformation. Now, so now if we want to look at, just to get some numbers, what are some differences between the activation stress for loading in basal slip versus pyramidal slip? So these have been characterized previously, and we can see that, for instance, something like magnesium, just pure magnesium, that we see a large 80 megapascal difference between an easy slip system and a hard slip system. So if your crystal is oriented that it necessarily needs to deform by this mode, it's going to be rather harder than if it's oriented so it can be accommodated by this mode. Similarly, just for another case, zirconium is also HCP, that it has an even larger gap in the absolute sense. You see 140 megapascal gap. Now, where twinning comes in is that when you have these large gaps, then there's this possibility that you can have an alternative deformation mechanism that's invoked. And deformation twinning, for many reasons, has been shown to be an easier mode of deformation in these cases where where slip to accommodate the C-axis is very hard. So where deformation twinning comes in is that it is a way of accommodating C-axis deformation, whether in compression or in tension. And so here I'm showing just an example of a deformation twin system where we can think about it in the same way we think about it as slip, is that there's a precise or slip plane or a twin plane in which twinning will happen, and in a particular direction in which will happen in that plane. Now I'm just showing one example, but it is a way of accommodating the same kind of deformation that pyramidal slip is. But if in the event that it's easier to activate this twinning system, then it will occur in lieu of slip. So just to give you an idea of different metals, this is just making the point where is that the activation stress for twinning has been quantified. Now, I wouldn't say that these numbers are precisely what would accommodate or activate twinning at the atomic scale, but as far as I put this up here, mesoscopic, on the bulk sense, when calculating what values would twinning be activated in order to explain these anisotropic behavior of these metals, we find that it occurs somewhere in between the easiest slip system and the next hardest slip system. So twinning it must be that from manifestations of how much twinning occurs in materials, that it must be the second easiest mechanism to accommodate deformation. In particular, it offers a way to accommodate C-axis deformation. So this is one reason why in HCP metals twinning occurs rather easy. It seems to be the second easiest mode of deformation. But one thing that's different about twinning than slip, everything we've seen here is there's a particular plane in which it activates in a particular direction, which seems familiar to slip. But one distinct difference is that in twinning, it only occurs in one direction. It's a unidirectional mechanism. You can't, it's not what you can have. The activation stretch is more or less the same in one direction as is other. So the forward and reverse direction are similar. But in twinning, that it's only occurs in one direction. So what happens is that this now explains why when twinning is activated in a material, that that the material then responds in a highly plastically anisotropic sense. So, for instance, we just can take any kind of rolled polycrystalline sheet of material, whether it's a magnesium alloy or titanium or zirconium. They all behave in this similar way, and when they twin, what kind of differences they can have. So if we were just to take a polycrystalline sheet of any of these materials and we were to then, let's say, deform it in, as we show in the arrow, in plane tension, that the response that one would get would be this a stress strain response in red in each one of these figures. So you would recognize these stress strain responses as being signatures of slip. You see that you have a yield and then a slowly reduction in the strain hardening rate as we continue to strain. Now, however, if you were to then reverse the direction of deformation. So you start a new test, you have the same sheet, and you deform it in plane, but in compression, then the response would be the blue curves in each one of these cases. And you can see that it's remarkably different, again, in the amount of strain hardening behavior and in the yield stress and in flow stress. So dramatically different responses happen when a material tends to twin just as easily as slip. Now, how do we know that twinning is happening? As I mentioned earlier, that twins can be seen through microscopic analyses. So these are maybe rather tiny images, but at any point in this curve, one could then look at the material and see that there's these fine twins that are occurring within the grains. And you can see it's not occurring in all the grains, and it's not really engulfing the grains either. So it doesn't really take that much twinning in order to have this effect. Now, so now to go into some basics of deformation twins, I first just want to contrast this with slip. So something you've probably, just a bit of review from last week is that if we think of a lattice dislocation, simple, I'm taking an edge dislocation where we have our extra half plane hitting on the glide plane. And if we were then to apply a shear stress such that it's resolved on that plane and in that slip direction, then we would force that dislocation to move. And if it were then to leave the crystal, we can see that it has displaced the top half of this crystal with respect to the bottom half by a lattice translation vector, or the Berger's vector. And so this is a perfect dislocation. We call it a perfect dislocation because in the wake of that slip event, that the material is still retained its ordered atomic structure. It's not fault of the material anyway. And then because of that, then a dislocation that's just like it is free then to deform right behind that dislocation and incur more slip. So because of that perfection, dislocations can then just deform one after another on the same slip plane and in arrays. And we often see that in metals that slip, is that if we can catch a dislocation array, usually at some boundary in which it's stopped, we see that we just have dislocations falling one after another. Now, so twinning dislocations are different than slip dislocations. So like slip, there is an elementary defect called a twinning dislocation. Now, they differ in that they have a step to them. Not all of them. Most of them have a step height. So the amount of Berger's vector, the amount of displacement incurred at the core of that twinning dislocation is spread over, think of it spread over more than one crystallographic plane. So here I'm taking, for example, representing the most common twin in the HCP class of metals. And again, it has a particular slip plane, a twin plane, and a particular twin direction. But if you think of this the twinning dislocation at the atomic scale, you can see that the amount of shear that it incurs is spread over 2 planes, and that's for this particular type of twin. Now, also that Berger's vector associated with twinning dislocation is not associated with a lattice translation vector. So it's typically shorter, and so when that this twinning dislocation moves, it will reorient. It'll actually change the stacking fault of the material behind it, and so it does fault the material. The material is no longer in its perfect atomic arrangement, and because of that, that means that if you were to have another twinning dislocation glide alongside this first twinning dislocation, it cannot glide right behind it, but it can, however, glide on the next adjacent plane. So because of that, we see twins. If you have a twin, that how they will grow is that you'll have these sequential glide of twinning dislocations on adjacent planes. And as they glide, they reorient the material behind it. And we call it a reorientation, but what they're doing is they're creating a fault. And that fault changes the arrangement of the atoms, and that appears to be a change in the absolute orientation of the lattice. And so as they glide one after another, they build a domain that is now appears to be reoriented. It is also sheared. So here I'm showing now the case where we have again our perfect HCP lattice with our twinning plane and twinning direction. Now, if we were to apply a load, which is the rather large gray arrows, then we would invoke this twin to occur. It would then build a volume, and in that volume, it would be reorienting that. It would be changing the stacking fault, which would then rearrange the atoms such that it would appear to be a reorientation of the lattice. Now, that amount can be significant, enough that you can easily see it in an orientation map. So again, I'm using as an example probably the most studied twin in HCP materials, where in this case, what we call it the 10 bar 12 twin. It's named for the particular plane in which it acts, and the reorientation that it can occur is on the order of 90 degrees. So it's a rather abrupt and large misorientation across that boundary of between the twin and the matrix. So typically we think of that as a lattice change or reorientation of the lattice. So when a twin does form within a crystal, it does form a boundary with that misorientation that is precisely defined by that particular twinning dislocation. And also that twinning dislocation, when it moves, it's shearing the material. So it's moving those atoms via shear. And so it's not just a how should I say? It's not just a reorientation of the material without any type of shear. The shear is occurring, and that's what's accommodating the deformation, and that's how why twinning gets invoked. So I just showed you an example of one type of twin, but there are actually many different types of twins, and we call them twin modes or twin types, if you will. And so the one that here I'm showing, there's about 7 that have been observed, and they have fallen into 2 classes. And in one class, there's 4 of them, and they share the same what we call shear zone or twin zone. And the one that I haven't discussed it, but it hasn't been. These twins here have this are as common, or some of them are common, some of them are not in some materials. For the materials I'll be discussing today, they are not as common. Now the more common one that I'll talk about is this one here, this kind of light blue one. This falls in a second class that has a shear zone that's along the A-axis. There are other types of twins as well. Now, all 7 of these are important in that they do have some key distinctions, which I'll go over here. Is that first of all, you notice is that there's a particular plane in which they act, and that means they have also a different twinning direction. Now, along with that, they have different step heights, and they do have a different characteristic twin shear. So there's a different amount of shear in which each will invoke. Also, they, and again, they have a different height to them, which means that there's a different amount of lattice or rearrangement that they will cause. So for each one, they're distinct in their twin matrix orientation relationship. They also are classed by the shear zone in which they have in common. And also each one has a particular direction in which it accommodates. So some of these will accommodate a contraction of the C-axis, and some will accommodate an extension. But you won't find one that will do both. So again, they're unidirectional type of deformation mechanism. So here I'm just showing, for instance, taking these 2 twin modes. This is what this one has activates on the 10 bar 11 plane in the hexagonal crystal structure. Here's this other one that I've been talking about, 10 bar 12. They share the same zone axis. Now, just to give you an idea of some numbers about how different they can be, in this case, this particular twin plane is a compression twin. So it will, when it gets activated, it will contract the C-axis. So in order to activate it, one needs to take the crystal and deform it in compression in order to have this be a possible mechanism to accommodate that compression. So in this case, the characteristic twin shear is about 13%. So that for magnesium, 13% is certainly a lot of strain to be invoked within a fine atomic. This happens to be 2 step heights. So within 2 crystallographic planes, you get a shear of about 13%. So this is for this 10 bar 12 plane. The reorientation, as I mentioned earlier, is close to 90 degrees. So it's rather large. Now for this other twin, this is the compression twin. That the amount of characteristic shear is even larger. So you can see that this is about 3 times larger. It's 40% shear, and also its step height is about 2 as well. So you get a lot of shear happening within just 2 atomic planes with this twin mode. So they're very efficient ways of accommodating deformation. Now the amount of orientation is also large, about 56 degrees for the misorientation. Again, these are also for just magnesium. They change a little differently when you have different C to A ratios. Now, as far as I just want to also mention that that twins do have variance. So within each type, you can have different variants of twins. So if I were to just, let's say we take just again, this HCP crystal structure, this dark red plane, I'm just marking as one particular plane. But if we now want to look at the 6 possible variants of the 10 bar 12 twin, we have them drawn here. This is the first variant, second variant, third variant, fourth, fifth, and sixth. Now, where these come about is because of the hexagonal crystal structure of this lattice. So in a sense, that just geometrically identifies that there are 6 different independently oriented twin planes due to that symmetry. They have the same crystallography, but just different orientations. And so that means that because of this, that anytime you have a twin mode in the HCB structure, you automatically have 6 variants. So all the 7 observed twin modes I mentioned earlier have 6. Now, so as far as twins, we recognize them as mesoscale structures in often when we do microscopic analysis. We will go into more of the atomic scale and the larger scale later, but at this point, this is where the mesoscale is an important scale for twinning, because that's when it's really starting to make an impact on the macroscopic properties of material, and where it starts to making I would say a larger contribution towards accommodating deformation. So how do they accommodate deformation? So first of all, as we've learned, that they do manifest as 3-dimensional domains within a crystal. And you can see here, I'm showing this orientation image map of magnesium that's been deformed. You can see there's many different twins. These are these lamellae. Now I'm showing you because of their describing them because of their shape, but they have been analyzed in the sense of what their matrix twin orientation relationship is across this boundary. And because of that, you can identify the twin type and its twin variant. So one thing that you don't see, that you can't really quite see from just orientation map, is the amount of shear these twins are actually providing, but it can be calculated. So, and because they have this precisely defined crystallographic shear, so they do provide an unidirectional shear. The relationship is rather simple. The amount of shear is equal to the characteristic shear, twin shear, times that volume that you see. So the larger the volume, the more shear that twin is providing. Now, if you wanted to then calculate how much the deformation rate that's being provided by that twin, that then depends on the rate that its boundary is migrating. So that's how twins will accommodate the deformation, is that after they form, in order to accommodate even an increment more in strain, they have to move their boundary. They have to grow. So you can see here that this twin in particular has grown to be rather thick and is accommodating a lot of shear within this grain. This one, not so much, but the shear rate is then dependent on that product of the twin shear and the change in its volume. Now, one thing you notice is that the twin shear doesn't change with time. The twin shear is fixed. And so that actually leads then to some interesting points about the fact that because this twin shear is fixed, you imagine that the most that this twin can accommodate for any grain is for it to completely engulf that grain. And still, it would not accommodate 100% of the deformation of that grain. So twinning itself, with just one twin and one twin type, cannot accommodate the full amount of strain for grain. So you would need to also have either other twin variants forming, or you would need to have slip. So other deformation mechanisms have to occur. So typically, it's not something, because of the fixed twin shear, it can't be the only deformation mechanism. There's also, because of its finite domain and boundaries that it introduces, that twins do have what I would call latent effects on slip. So because they introduce a boundary, this boundary can be a barrier for slip to occur. So if slip is occurring in the same grain, which usually it is, then it then tends to act as a directional barrier. So for some slip systems, so it can change the slip activity of a grain by making it difficult for one type of slip system to deform relative to another. They also, as I mentioned, that because of the fault changes that they create, that there is a different orientation of the twin with respect to the loading. So once a twin domain has formed, then it's possible for new slip to occur within that new twin domain. So twins, when they occur within a grain, they do have some very strong on the slip activity that's occurring also within that grain. Now, so just to kind of go over some manifestations of twinning that we see, and this is, I have pictures of HCP metals, but it's a very similar thing in other metals as well, is that twins usually don't occur in this nice single pattern of one twin within a grain that we use to study. Is that typically they have very complicated structures when they form. So so as I mentioned, so many times the twins can be seen by orientation image microscopy, OIM. And so some of these here are EBSD maps of, excuse me, EBSD maps of deformed materials that have seen a lot of twins. And just alone from an orientation map, you can obtain a lot of information on twinning. You can find out, of course, their shape. And that includes its thickness, volume. You can kind of suppose if you know if it's a columnar structure, for instance. You can also determine the mode because there's only 7, and that just by looking at the misorientation across that boundary, that automatically defines what twin mode this twin belongs to. And within that mode, you can also identify the variant of that twin. Now, you see that they also take on different types of configurations. Once deformation is applied, it's oftentimes that you'll see many parallel twins within a grain. For instance, you have this grain, you see many twins that, because they're the same color, they're the same variant, the same type, and there's several of them within one grain. They also can be intersecting, so you could have the same mode but different variants. And so because they're different variants, they would be intersecting within the grain. There's also something called double twinning, where the twin domain will act as another domain in which you can have twin initiate again. So this is an example here where all the red areas are primary twins, and then the blue areas are new twins that formed within those primary twins. And then you can have something called what we call twin chains, where twins aren't necessarily confined to their particular grain, but they can cross boundaries and move from one grain to another. They would necessarily be different types, not types, but they would be different twins, but they could be of the same variant and the same type, but particular for that grain. Also, there's something called detwinning. So if you were to reverse the applied load, then locally on every grain, the loading would be reversed. Now, twins don't move in back and forth manner, but there's something called detwinning, where you would see a disappearance of that volume. And that usually is because another twin has occurred within it that's changing, reverting it back to the original lattice orientation. So, or maybe if you have a twin front where the twin is moving by facets, which we can, if we have time, we can get into that later. But those type of defects can move back and forth, and that is another mechanism that's being proposed for deformation twinning. So just one last point about deformation twins at the mesoscale is that not only are the configurations variable, but also we find and have long known that twinning is highly statistical in its occurrence. So what I mean by that is that it's hardly a deterministic problem when dealing with when twins occur, what type of twins manifest, and where they occur. So this is just to point this, just one slide to point this out, is that recently there was not recently, about 10 years ago, there was a study done where we took advantage of the automation that we can have with EBSD. And so we taken material, just a common pure magnesium, had done several amounts of metallography on it, and we performed a statistical analysis just to identify what grains would twin and what size grains would twin, what orientation of grains would twin. And so in the statistical analysis, we included over 2,000 grains. Within those 2,000 grains, this material was heavily twinned, so we had 8,500 twins, and the percentage of those grains that contained some twins was more than half. And excuse me. And so at the time, sorry, I'm not. At the time, many of the models that we had, sorry for many of the models we had for identifying what grains would twin and what are the properties of grains that would tend to twin more in a grain and then in a material than another. Oh, sorry, I have something. Sorry, I have something in my throat. Were typically based on size. The idea was that grains that were bigger tended to twin more than grains that were smaller, or some grains that were preferably oriented than other grains for twinning. But as long as the grain had the same orientation, all those grains within a grain would twin. So all grains within a polycrystal that had the same orientation would twin. So recently in identifying twins and correlating them with their parent grain properties, we find that a lot of that was not true. That many of the grains that would favorably be oriented for twinning did not twin. Many grains that we would think never would twin because their orientation was so poorly oriented for twinning contained a lot of twins. Some of the variants that the variant selection criteria was based solely on just a projection of the load onto the twin plane, and so the highest Schmidt factor twin would be the one that would be expected to form within a grain. However, we find that in most cases, 60% of the cases did not follow that rule. And so on and on and on. So the point being that it's determined that what we see here at the mesoscale is not largely going to determine which grains manifest. So there's importance in the atomic scale then of determining which grains get selected for twinning and which twin types get selected, etc. So then that kind of brings us now to analyzing the different stages in deformation twinning. So here is just a general breakdown of the stages of twin development. Very simple. You basically have birth and some life, and then eventually some growth. So the first stage is nucleation. And so twins do begin at the atomic scale, and they can nucleate somewhere within a grain or at the grain boundary. So where they nucleate and where and in what size and critical size at which they nucleate is currently an area of study. But they do occur at the atomics. They do start at the atomic scale. And then the next stage in twin development is what we would call the propagation stage, where it now moves from atomic scale, an area that, of course, presumably is very difficult to see, to now starting to the micron scale when an embryo now forms and elongates into a lamellae. And this is what we call the propagation scale. This can occur anywhere between the nanoscale to submicron. And then you now then have the largest scale, which is submicron to micron, or just the grain scale, where now the twin has come across or span the entire grain, and now it begins to thicken. And so this is where the area that I was describing the twins most often. This is the area where we can start to see this is where twins are accommodating deformation, when their boundaries are migrating within the grain. Now, just some observations. This is some cartoons, but just to give you an idea of what these type of stages look like in the microscope. So as far as nucleation, here I'm showing you a twin embryo. This is about 40 nanometers across. This happened within a crystal. As far as propagation, here's some snapshots. I believe this was an in situ study where they had seen a twin emanate from a boundary, and it's just propagating into the crystal like a spearhead. And then there's the stage where the twin actually now spans the grain. It's now connecting with all the grain boundaries within the grain, and it now begins to grow. So this boundary starts to grow in thickness. All right. So there are other, as we've seen by the type of configurations that can occur, that growth is not just solely the only mechanism for growth is not just slowly a thickening or widening of that twin, but there's other mechanisms by which the twin can migrate its boundaries. So remember that the only way a twin can accommodate more deformation is by thickening or growing or increasing its volume in some way. So self thickening is one way, but it can also propagate across boundaries. So we call this twin transmission. That can then invoke a twin in the neighboring grain. Also, you can have many twins within the same grain. They're what we call parallel twins. Sometimes you can have multiple twins of different variants, different types, which means that because they occur on crystallographic planes, that means they will be intersecting. So they form junctions, and then also, as I mentioned, you can have double twinning. So these are all ways in which the twin will grow under stress and accommodate more deformation. So some of the big questions then become, how are these different mechanisms accomplished? They will have different activation barriers, and they would be also dependent on the local environment as well. So as far as nucleation, let me see, how are we doing on time? So, okay. So as far as nucleation, we can now just focus a few slides on this. What has been observed is that twin embryos have been observed, and they appear as these like seed-like or ellipsoidal type shape embryos. So here, this is actually from 1997. This is a HCP crystal of zinc. This is you can see this is our 10 nanometer scale. This is about a 80 to 90 nanometer diameter twin embryo within a zinc crystal. Earlier I showed you, this is from some of our work where we had a magnesium pillar, and we saw this formation of this nice embryo occurring within the pillar. Now they don't solely happen within the crystal. They can also happen at surfaces. They've been seen at crack surfaces. For instance, here's this small little twin embryo. The boundary is outlined. Here's what it looks like without the boundary outline. So that's one manifestation. Here's some of some earlier work where we saw the development of twins from just a perfect boundary, just by hitting it with a pileup and seeing twin seeds forming at a boundary. So they can, so in addition to crack surfaces, twins also can be seen at grain or forming at grain boundaries. This is another recent work where this is a twin boundary, a pre-existing twin boundary, and then under subsequent load, another twin nucleus of some other type of twin has formed. And so what I want to impress upon you is just this sort of a seed-like or ellipsoidal shape of these twins. And they do start off as these finite size, some embryos. Just as far as trying to nucleate them, they do nucleate under high stresses. So this is actually I've already showed you some examples of this work, but this I thought was nice. It's very recent work where they had deformed a single crystal magnesium pillar. And just right here in the middle of this pillar, after some amount of deformation, they see this twin nucleus, and you can see its shape. It's just this kind of seed-like shape. And as with more and more deformation, it's starting to kind of pierce out and elongate into a lamellae. Now, some of the more common observations, if you don't have a single crystal pillar and you have a polycrystal material, is that they would prefer to form at grain boundaries. So here is I took this from, I thought this was nice in situ work. At the time, this was in situ EBSD, is rather new. We see here we have magnesium cerium material. This was clean of twins when it started, but these researchers had formed this material in situ, and forgive my sort of cartoony way of pointing out what they've done, but this was an in situ EBSD, and they had seen after some amount of strain that these twins just started to nucleate from the grain boundaries. And you see then with more strain, rather than having them continue to propagate, they saw new ones forming. And then later on, with more strain, they saw even newer ones forming, and then those ended up growing to be very thick and then accommodating deformation. Also, here's just a nice TEM image of just some twins, and they're also embryonic stage forming at a boundary. Here's a sort of a dual twin formation where you have twins forming, and one twin forming in each adjoining crystal at the same point in the boundary. So what this tells us as far as understanding nucleation is that the activation volume is rather small. They form in high stresses, and if there is a crack or a surface or a defective boundary, they tend to form it at those defective regions. And so it's a very small scale process. So as far as some theory, there hasn't been a lot as far as theory of twin nucleation for HCP metals. How it differs from other materials is that we see that this embryonic stage is of a twin nucleus, which is not necessarily, which is a lot larger, I would say, than a critical nucleus for FCC or BCC crystals. So for HCP, we see this embryonic stage forming, and it contains many defects. So if I were just to then review some earlier work in the late 60s of trying to understand twin nucleation, largely it was based on some of the early work in FCC as well, where you have to obey two types of principles. One is conservation of Berger's vector, and another is also energy. So the energy favorable for forming or breaking or forming twin partials. So here's how it works is that you have lattice dislocations, you have a defect. So this is heterogeneous nucleation. And a lattice dislocation, for instance, is gliding along, and for some reason it stops, it becomes stationary, gets activated by a large stress, and then disassociates into an immobile residual dislocation plus a twinning dislocation. So this twinning dislocation is now what I referred to earlier. It can glide on a particular twin plane in a particular direction. And so in this case, this twinning partial was produced by the disassociation of a lattice dislocation. Now, so there's two principles again that have to be obeyed. One is conservation of Berger's vector. So the sum of these two vectors, the residual and the twinning plane, have to equal the original defect that was disassociated. And so depending on how large that defect is, you can get a number of twinning dislocations N. Also, you have to follow that it's an energetically favorable process. So here I have the core energy that's needed to break that dislocation. That is necessarily obtained by atomistics. But then you also have to have the interaction energy between the residual and the twinning partial. Those have to be repulsive, so that once that disassociation happens, the twinning partial has a repulsive interaction with that newly formed immobile dislocation, and it can move away. And of course, you have to then, as this twinning partial moves, it creates a stacking fault, which is then energetically expensive. But then you also need to put the work in. So when you run through these, and we did some work on this where we took this idea and we just moved it to 3D. But the point ends up being the same, whether it's a 2D or 3D model, that you need a lot of stress in order for this disassociation happen and produce a certain number of twinning dislocations. So the idea then became that in order for this high stress to happen, you would need one of two things. You would need, for instance, you would need a high stress, like let's say formed by a pileup. So if you have a large pileup of slip dislocations, that first dislocation at the head of it that's stopped can experience a high enough stress, it can disassociate into multiple twinning partials and then form a twin. So then became the idea, well, we need you need a lot of stress, but then you also, in order to form a large number of twinning partials, you need to also have large dislocations with large Burgers vectors. So one idea was that grain boundaries tend to be defective. They tend to contain larger defects, much larger than, let's say, a lattice dislocation. And so, and they tend to also have fluctuating stress or high stress concentrations because they either are stopping pileups of lattice dislocation. So the idea is that if you do have a boundary, let's say, between two crystals, it contains some grain boundary dislocations. Under a high stress, these dislocations can disassociate and form twin seeds, and then they can coalesce and into one twin embryo, let's say. Now, that's conceptual, but of course it's good to test this at the atomic scale. So thanks to molecular dynamics simulation, we do have this possibility to see if something like this could work. And so in this particular work, we had taken just different types of grain boundaries called symmetric tilt boundaries, and these depending on the amount of tilt across this boundary, they can have a certain spacing of defects, certain Burrs vectors of those defects, and typically the larger that misorientation, the more defects that you have, and larger grain boundary defects. So if we take, for instance, the larger case here, this is almost 30-degree misorientation. There are these colored regions here are just pointing out the areas where you have the larger grain boundary dislocations. And so under simulation, these boundaries were then hit with a dislocation pileup. And as we can see in time, that we saw this formation of these twin seeds, if you will, which then proceeded then to coalesce under more deformation, and then they just grew larger and larger, forming a twin embryo. So as far as experimental observations, you can see this is quite recent, where this idea was then experiment, I would say, was devised to see if how this would manifest. And so in this case, it was kind of interesting. a thin film of, I guess, magnesium single crystal was deformed. A twin was created within that single crystal, and then a thin film was cut from it. And the idea was then to deform it subsequently under locally under using a probe, and just to watch it grow, to see how it would grow and how twin boundaries would migrate. So this is just showing you the setup. Here is the thin film. Here's that pre-existing twin. About 500 nanometers from that twin tip, a needle was used to press locally on the thin film, and it happened to be along the A-axis of that film. So what was found was two things happened. Is that, first of all, that twin tip did advance, and it moved forward, but it didn't widen. So it didn't get thicker. It just sort of started to migrate across a little bit. But what was interesting, however, was that a second twin nucleus formed. And so so this was the second twin nucleus is a different twinning type. It was what we call a contraction twin I had shown earlier, where this was this 10 bar 1 twin along this 10 bar 1 plane. It when it deforms, it accommodates contraction of the c-axis. So evidently, when this subsequent loading was occurring on this thin film, that the stress state was such that it was compressive along the c-axis, and so this locally was forming this a compression. It wanted to form a compression twin instead of propagating the original twin. So this is just showing a close-up, just to prove that it is this particular variant in compression twin. But what, in lieu of the actual in situ video that they had, what they found was that it started just like we had seen in the molecular dynamics simulation, where a little twin embryo had formed, and then with more strain, a second one formed next to it, and then with more and more strain, it started to coalesce, and forming this kind of interesting shape. So so that's kind of a brief review on nucleation of twins. I thought we would take a 5-minute break in case everyone was, but I think given the time, we may not do that because we're close to. But also, if I can take any questions anyone may have. I was just going to move to propagation, if no one has any. Okay. So now the second stage in twin deformation is from moving from nucleation to propagation. Now this is an interesting phenomena where we see that once they've formed an embryo, they change shape, and that shape is almost like a spear or a wedge shape. And you can see some of these captured in these EBSD maps. This is of titanium, where just very early on in the stages of deformation, if you catch it at the incipient point, is that here's just this one grain just formed initially just one twin, and it's emanating from the boundary and moving out into the crystal. Here's a second case where again you see this twin that's just formed and moving out. So it's giving this, just like we saw earlier in this in situ EBSD, that they seem to form just at the boundary and then just move out ever so much, and then terminating somewhere in the crystal, and they form this kind of a wedge-like shape. So then, and something else that's also then noticed is that they seem to, as they grow, is that they don't thicken so much as they just sort of propagate straight into the crystal, and usually with relatively rapidly. In understanding this next stage, something that has been useful is to develop models that would represent these discrete twin volumes within crystals, and to then determine what are the stress fields in and around the twin as it's deforming and moving in a crystal under deformation. So before that, I wanted to just review one point, is that when you have let's say you have a microscopic image such as this one, where you see many twins, you see the shapes, you see the volume that they take up, but you don't see how much shear they're actually providing. And so with this, with this cartoon, I wanted to show, say that you have a single crystal of an HCP material. This is the C-axis. Now what we've drawn here is a twin that's occurring on the 10 bar 12 plane, and it's got this certain volume. And because this is a single crystal with free surfaces on the side, you can see how much shear it is invoked. And then with that, the change in C-axis extension that it has produced. So with this twin forming from one side of the crystal to the other, we see a shear, and we also see an extension of that C-axis. So now if we imagine then that if it's a twin that's within a crystal that's within a polycrystal, then we have some neighboring grains to this grain that just has a twin in it. And these grain neighbors will impose resistance against that shear. So as a result, they will experience a stress concentration, almost like as the tip of a crack, a shear crack. And at the same time, because they resist that shearing, the grain with the twin will experience what we call back stress. So there'll be a forward stress and a back stress that's resulting from that production of that finite domain with shear. Now, I'm going to show you some examples of calculations that we did, but I want to impress upon you that there are other methods that have been developed in recent years to calculate these stress fields around twins within crystals, and they have ranged from using finite element solvers to fast Fourier transform solvers to dynamically simulating the formation and growth of twins within a 3D structure. So it's getting quite interesting. So with this, I'm just going to give an example where we have this. This is a three-dimensional crystal. We have a single grain. We've kind of modeled the outside just to be some homogeneous polycrystal here, but just we're going to focus on this one grain, and it's going to be a single crystal with its C-axis upwards. So if we were then to imagine that that we were then to put in a twin, so we would have this twin domain. It would be terminating within both its tips within the single crystal. It would have the orientation relationship of that twin. It would also have the shear, the characteristic shear that we would expect. And we can just see what would be the stress field around this type of twin. And we can, with the stress tensor, we can take any component that we can take any component and map it out. And for this, we choose to, what I'll show in a second is we choose to calculate or project the stress tensor that's calculated onto the shear plane in the shear direction. We call that the twin resolved shear stress, just so we can get some idea of what would cause the twin to grow. So if this twin resolved shear stress is positive in the proper direction of twinning, then and it's intense above a certain activation stress, then twinning is possible. It is, of course, if it's a negative value, then as I mentioned, it's not going to promote twinning, because twinning is a unidirectional mechanism. So just here, here's a calculation. Here, what we're showing is this crystal within this is an effective medium polycrystal. We have a applied far field load. And under this load, we can see we're just coloring here this twin resolved shear stress. And it's about, on this scale, it's about 20 megapascals. So as we see here, it's pretty uniform. It's nothing special. We haven't added the twin yet, so we've deformed it. And just like we would in an actual material, after some amount of deformation, a twin's going to form. So we place that twin in the middle of the crystal with its shear and reorientation, and we find that we then generate a highly heterogeneous stress state. So and again, what we're plotting here is the twin resolved shear stress. So anytime we see red is when the twinning resolved shear stress is pointing in the positive twinning direction. And if it's intense red, then it's an intense amount of stress. So given that 20 megapascals was about the stress that was uniform in the material before we invoked the twin, that here you can see it, that you get this high stress concentration above that value. And so with that, that would suggest that just by forming that twin under that stress state, it could self-propagate forward at its tips and easily then get to the grain. However, as far as at the twin boundary, within the twin domain, and then some distance from the twin boundary is the yellow part, that the twin resolved shear stress is anti-twinning. So then that along the twin sides of the twin, along the twin boundary, that would not promote a widening or a thickening or more or migration of that boundary under the current stress state. So this then suggests that twins, or helps explain like the twins, that once they form, they tend to grow anisotropically at their tips, and they don't thicken as they elongate. Now, when they actually will thicken maybe we'll get to that later, is once they've actually hit a grain boundary, then they don't have any choice after that. So so with that, this kind of gives you the idea that this is largely what I had said earlier, is that in a way that twins, they propagate just by moving it from their twin tips, and they promote lengthening, but not so much widening. So with that, I noticed that we are close to the end. I will leave off here then. And I understand that we will be having a lab session later on Thursday. So I have prepared what I thought would be a couple of questions that we could go over. So for Thursday, we can go over any questions that anyone may have. If they also see this later on YouTube, we could discuss that. Also, I thought we could have a nice discussion on twinning itself and how it relates to slip. So I have a couple of questions we can go over. One is to identify at least 3 ways that deformation twinning is different than plastic slip. Also, to list and discuss at least 3 types of slip-twin interactions. And also, finally, to describe 2 or more ways properties of deformation twins can affect the macroscopic response. So with that, so anyone that happens to see this today and wants to join on Thursday, so be happy to see you there, and we can discuss these 3 things. So again, thanks for your attention, and hope you learned something about twinning that you didn't know before. So
thank you, Irene. The floor is open for questions. Since there's not too many of us, I suggest if you have a question, please unmute yourself and simply ask it. So actually, the first question has already come in over chat, so I'll just read it out, and Irene, you can take it. How does the twin nucleation mechanism depend on the grain boundary structure and strain rate?
Okay. So that's a very good question. One thing, at least we can find from the basics of what we know about twin nucleation is that you need a high amount of stress and or a highly defective area. So so you need a way. In heterogeneous nucleation, there needs to be a defect. So as far as grain boundaries, if you have, let's say, a perfect grain boundary that's coherent, I would say perfect in that it's a coherent grain boundary where you don't have any intrinsic defects. This would be a poor boundary for nucleating twins, because it doesn't have any triggering or initiating large defect that would in which a twin can form. So highly defective, on the other hand, a highly defective grain boundary would be ideal then for nucleating twins. Another thing is you also see that there's a coalescence process as far as when the twin moves from forming a stable twin embryo to then being able to propagate into a perfect crystal. So there's a certain critical size. Can't say I know what that size is, but the important point is that there is a critical size. And so the more defective your boundary, the closely neighboring defects, then you can see that then that could enhance or promote the formation of a sufficiently large embryo. Now, as far as strain rate, the tendencies that people find is that when you have high strain rates, such as of interest in CREDDS, that twins are more likely to form. Now, twins move a lot faster than slip dislocations. And so you can see then with higher strain rates, when you have smaller time scales, twinning becomes a more favorable mechanism, because it's easier and faster to move. The only cost is that it does require a high amount of stress, more so than slip. But when you have a high strain rate situation, typically you have the stress that you need. So that's I hope that answers the question. Hello?
Additional questions? Can twins be observed in X-ray diffraction patterns?
Yes, they have. People have actually used that to determine when a twin will form, and as far as the type and if you know something about the type and variant, those you would need to have something like more of a microstructural framework. But when they happen, I would think theoretically you could identify when twins happen, but not so much. You would need a certain threshold of volume before you can identify how much twinning you have. So it's typically the rule of thumb is once the volume fraction of twins is over about 15 to 20%, then they can be detectable. But it's if you want to know, but by the time it's detected, you pretty much have a lot of twinning. So we find some of the best ways to understand incipient growth is going back to more of a microstructural specific framework, like microscopy.
So the next question is, what kind of size effect do twins have on mechanical properties? For example, how would it be different if you had a large number of embryos versus a large number of full-grown twins?
So if you have a large number of embryos, then you mean that so if they just remain embryos, but you have the same volume fraction of embryos as you do one twin, that will make a big difference on slip. In that, with the small embryos, you will not affect slip activity to the extent that could be seen in macroscopically. However, if you have, let's say, a grain that is engulfed fully by a twin, that grain in a way is going reoriented with respect to the loading. It will then invoke different types of slip. And if it's an HCP crystal like we're describing, then changing the orientation of that crystal will affect the response, will affect what slip is activated. So once a grain is completely reoriented by twinning, it could invoke another type of slip. It could invoke another type of twin, and that will likely be more detected macroscopically than to have many small embryos. Because within an embryo, you cannot sustain any slip or would not affect slip as much at all, if at all. So these are good questions. I think if anyone thinks of any more, these are some of the areas that I hope to discuss this Thursday.
So actually, there are a couple of questions in the chat box. If Michael can go there, there are a couple more.
Yeah, I've already read those out.
Okay, so
you missed some questions.
Oh,
right.
Did I? Oops, I'm sorry. I missed a few questions. Let's see. Okay, so here's another question. What is the time scale from nucleation to lamellae formation?
No, the time scale, I don't know the answer to the exact time scale, but what is seen as being there's two processes. One is that first you have nucleation, and you need to have the time to create an embryo of a certain critical size. So there's one time scale. And then once that critical size happens, then there's the time scale to propagate it. Now, if you have a perfect crystal so that there's not any hindrance from propagating across the crystal, across the grain, then it depends then on the driving force. So sometimes the driving force for it to propagate or to grow an embryo is favored more so than for it to propagate inside the crystal. So have you seen that in some cases where you have twins that will have found it easier to grow within a grain boundary, but then once they propagate into a wedge-like shape, they stop. Whereas others where they once they're forming at the grain boundary, they quickly move across. So there's not a one answer to which one's faster or slower, but it has a lot to do with the driving force locally for a twin to happen. So if it's the resolved shear stress is enough for locally to have it propagate across versus having it grow in the embryo. So there's two different stress states that control that. So growing the stress state to grow the embryo in a grain boundary, let's say, is different than the stress state to have it move across a grain.
We have another question. How does the sensitivity to temperature vary between twinning and slip, and why?
So the sensitivity, what is generally expected is that slip is more sensitive to temperature than twinning. Now, this is an idea that comes about because slip is thermally activated. And so in order for a dislocation to move, it moves by thermal activation. So for twins, this type of idea doesn't apply. So so the idea is that twins do not have either well, I think, I'll tell you what I think. I think that they do have a temperature sensitivity, but it's not for the same reason as slip. And so for the first of all, one question that is to think about is that why would slip dislocations twin at all? Because as we've seen is that you need to have some slip activity before you have twinning. So slip, if a material can deform by slip, then it will. But there's some type of process at which it transitions from slip to twinning. So as far as temperature, if the temperature is high enough that slip is favorable, and it can keep moving and it's mobile and accommodating deformation the easiest way, there's no reason to transition to twinning. But then if the temperature is not as favorable for slip, then it gives the opportunity for slip to then become stagnant, to become slow, and then high rate or high stress dissociation processes could happen that could transition the slip to twinning. So if there's situations where slip is difficult, which is such as like in cold temperatures, then twinning then becomes a preferred option. So then, so slip is, twinning comes from slip, and slip is a thermally sensitive process.
Okay, we have a few more questions. First one concerns page 17, and it asks about how to identify twinning. Is it simply because you see a needle shape in the image?
So the fortunate thing about twins is that they are precise in their misorientation, and so the way to identify twins is by the twin matrix orientation relationship across their boundary. So it is not based on shape. So so one needs to, in order to with shape, you can kind of get a sense that that must be a twin. But if you want to undeniably identify a twin, you need to identify the misorientation across its boundary.
Okay, if that's the case, for example, for the image in page 17 or 18, how did you recognize? I did not see, or say it's. So if you can go there, I did not see the thing you said. I just see a needle shape there. So, right. So for example, for the ABCD, I can see a needle thing there. So how to really recognize it's a twinning?
Oh, so here, well, let's say, so this here is a twin. Right. And so across this, the matrix is what I'm calling the grain, and that's red, and the blue is the twin. So you can't get this from looking at this image, but you need to identify the orientation of this grain and the orientation of this twin. And if the twin matrix orientation relationship satisfies, in this case, the 86.3 degrees misorientation, then that is a 1 bar 1-2 twin.
Okay.
Yeah. So you can't because I see so by looking at this, you can sense that, well, this is a candidate for a twin. Oh, this is a candidate. But okay. If you want to know what type, since there's 7 different types, if you want to know what type it is, you have to look at the misorientation across the boundary.
Okay, so one more silly question is that if this does not help us recognize a twinning, so why do people usually show this, in their paper or on their slides?
Because in this case, you can I mean, with this is one way to image directly the shape of these twins. So once someone identifies them, then you could then they will say, like, anytime you see this shape, we've already identified this to be a 1R1-2 twin. And we've now with this, you get this additional information of how they're connected, let's say. So you can say, well, this twin is different from this twin because it's a different color, so it's a different orientation. But you can see that how they're overlapping at this boundary. So that's kind of interesting information because that kind of can give you an idea where it might have started. Here you can see that this grain, this orange grain here, has got two types of twins, and here it has one that's terminated inside. So you can get a lot of this configurational information from looking at this image. So it is important to recognize that these are twins, how prevalent they are. But as far as the analysis, like once someone does the analysis, they can just then tell you, right? What kind of twins they are. Typically, what would be nice is if an image like this is accompanied by, let's say, a histogram of the different twin variants, the different twin types, or maybe like a misorientation histogram to kind of point out where you have spikes in certain misorientations that also can give you an idea or proof of the type of twins they are. But this is, I mean, this is just additional information on their microstructural features.
Okay, thank you.
Okay, two more questions. The lecture showed the stress strain curves are different under tension or compression. Generally, how does twinning contribute to the plastic strain?
So twinning contributes to the plastic strain by, oh, let's see, where did I have that? I thought I had. It's very simple. Actually, it's usually for slip it's not so simple, but for twins it's pretty simple. Fortunately, one of the simpler aspects of it is that it contributes to the strain by shearing on a particular plane in a particular direction, just like slip. But you see them occurring in volumes because once a twinning dislocation is passed, it needs to then move to the adjacent plane and then shear again. So how it accommodates strain is by shearing these volumes, shearing a finite volume within a crystal. And then how it accommodates the slip rate or the shear rate by twinning then occurs by its growing, by its propagating that boundary.
Okay, so may I say that if we consider a constitutive relation, I can just add this shear component to the constitutive relation? And also, actually, the V, the reoriented 3D domains, V is not a phenomenological variable. It's like it's a microscale variable. That how to implement this equation?
So this is a microstructural variable. So it does associate with one twin.
Okay.
Yeah.
Okay.
And but yeah, the slip rate, like if you have, let's say, crystal plasticity is a theory that relates slip rate on certain slip and twin systems with respect to the deformation of a crystal. And so activity we define by having a positive gamma dot or positive rate.
Okay, thank you.
And the last question is about the sensitivity of twinning to other imperfections and its influence on the statistical nature of twinning.
So if you have other imperfections like cracks, they also will, twins will, cracks, for instance, give a nice area for twins to happen because they do two things. They are defective, and they also have high stress concentrations. So those could be preferable areas for twins to nucleate.
Okay, so basically it's because you mentioned the statistical nature of twinning, and I'm considering usually for this sort of sensitivity, usually it's because of the imperfection that usually people cannot quantify. So people say, okay, it's because of this statistical thing. We cannot really precisely predict them. So I'm just curious about, is there any comment on this sensitivity to this imperfection that people cannot quantify?
Yeah, usually like, for like I see like, so like you have the statistical nature of like ceramics, and they have cracking and what becomes statistical about it is because where a crack will occur and when it will occur is in a way a rare event, because if you consider any point in the material at any time to have a crack, it has a very low probability. So similar with twinning is that where in the material and at what time in the material a twin will happen is not deterministic. It's not easy to define when and where a twin will occur. And so this becomes, gives it more of a statistical nature, and that that where and when it occurs is in a very small area and has a very low probability. So now, while this may look like a lot of twinning, it's not. Oh, sorry, I have another appointment at 2, so I think hold on. Hey, Sis, can you get the door? Oh. Hey, Sis. Hi. Come on in. I'm in the middle of something. If you don't mind hanging out till 2. Yeah. So have a seat. Yeah. Okay. Sorry, I'm back. So here is this. These results that we found were just manifestations that tells us that statistical, we cannot view it as in a deterministic way, because where and when twins happen and what variants they select, they're far from what we would predict if we were to say that there was a particular time, a particular place, a particular grain in which twins would happen. And so I can probably go into it in more detail on Thursday, but because of that, we kind of stepped back and started to look at the fine, small-scale areas where we've seen twins to occur. And so where that statistical process likely, or where it mostly originates, is right in this very small-scale portion, very small-scale area where twins actually first form. So yes.
Okay, thank you.
Yeah.
Okay, so this has been a very thought-provoking and stimulating presentation. Thank you very much for that, Irene. I think that we've got plenty of material to keep us going on Thursday, so we'll call it quits for today and look forward to seeing all of you then.
Yeah, and so thanks. I will. One thing I do have some references that there's not really a good textbook or that I know of on twinning, but there's certainly great textbooks on dislocations that include twinning. I believe like John Hurth's book, Hurth and Loda, and then Hull and Bacon. But we have some work specifically on twinning if there's some more interest in it. But yeah, I look forward to talking to you guys on Thursday.
Excellent. Thank you very much. Goodbye, everybody.
Bye.